Okay, thank you. So this talk will be excellent preparation for the previous talk. So when I'm done, you can teleport back and watch Guillaume's talk again. That was really good. So I'm Steve Adachi. I'm from the Lockheed Martin Advanced Technology Center in Sunnyvale. So I was really glad last year when the organizers announced that AQC would be at NASA Ames this year, because our facility is literally right next door to Moffett Field. So if you go outside, you can see my building from here. So it was a really short trip for me. And I was also really happy to see that there are an increasing number of talks this year about applications, because that's my area of interest. And so I'm going to talk about quantum machine learning. And since Alejandro's not here, I'll say what Alejandro would say if he were here, which is that it is very important to be doing benchmarking on real-world applications. And so, you know, I'm glad to see people thinking about that. And just for, and are you my countdown clock there? Or, okay, good. So yeah, just for a little history, 2.5 years ago, Seth Lloyd and Nathan Wiebe organized a quantum machine learning workshop at a mainstream machine learning conference at NIPS in Montreal. So that workshop was held in a room which is about 1/4 the size of this one. So back then, I felt like I pretty much knew everyone who was working in this little subfield of quantum machine learning. But that field has grown you know, so explosively since then. So there's lots of people doing good work that I've never met, and you know, probably who know a lot more than me. But hopefully you'll find something interesting in this talk. So for those of you who are physicists, I'll just give a little cartoon about machine learning. And so you know, we all, it's very useful in our daily lives now. So there's, you know, AI everywhere. It's recommending books and movies and friends to us. And it's telling us how to get places in our cars. Our cars are stopping for us. If you drive around Mountain View, you'll see self-driving cars. And so one of the key technologies that's enabling a lot of this is deep learning, which was already mentioned. But so what is deep learning? There's this, it's really applied to a family of different models, but they all kind of look like this cartoon here. Right? So you have a neural network which is multiple layers of nodes which are arranged to sort of mimic what we think is how our brains are organized. And so on the left, you have what are called the visible nodes. And so you have raw data coming into these nodes, which is typically high dimensional. So it could be, you know, things like images or text or speech. And then it is processed through this network, which has configurable connection weights. So those are really the parameters of this network that has to be trained. It goes through multiple hidden layers. It comes out the other end. So there's an output layer, which is low dimensional. And so this represents the categories or features of your data. So if you're going from left to right, you know, we call this discrimination. So this is asking, what is the thing that we saw, or what are its attributes, or to predict something about that. And if we go right to left, we call that generation, which would be, say, show me an example of this object, or of an object that has these characteristics. So this is what we try and do in deep learning. And you know, this technology is very successful using classical hardware. And so, for example, the AlphaGo system that beat the human world champion, you know, these systems are starting to achieve human-like intelligence. So as Guillaume already mentioned, in the unconference yesterday, we asked the question, does machine learning need quantum computing? And that's actually a good question. On Monday, Tamura-san from Fujitsu mentioned Moore's law, and so we know that, you know, ultimately there is this wall that we're going to hit But as far as deep learning is concerned, there doesn't seem to be any foreseeable end in sight. People are building, faster, more powerful hardware with GPUs, and now there's special purpose AI hardware. So I think that's a valid question. But then I think one way to look at this is that all these improvements in technology, it's really kind of a brute force approach. In other words, we're still performing as many operations to train these neural networks. We're just able to do them faster. So I think where quantum computers might be able to help is, can we work smarter instead of harder? And is there a way to achieve hybrid architectures where we offload some of this work to a quantum computer? You think of it as a machine learning coprocessor, and then in this hybrid architecture, maybe we can do fewer overall operations. And so that might enable us to prolong the lifetime of Moore's law and do these kinds of things more efficiently. So that's the way I think about quantum computing and deep learning. So at that conference back in 2015, I presented a paper about, so this is a very early example, and Alejandro and the NASA team also presented, and D-Wave at that conference. And so we were looking back then at examples like this using Boltzmann machines, which you just heard about. But I was particularly interested from a quantum annealing point of view, since I've been working with a D-Wave machine in this type of model. So this is one of the flavors of deep learning, and so the restricted Boltzmann machine really marries very well with quantum annealing, because as you've already heard, it's based on a joint probability distribution which has a quadratic energy functional, right, and stochastic binary variables. So there's a natural mapping onto the Ising models we use on near-term quantum annealers. So that was one plus. And then also the way these training algorithms work, they're very forgiving of imperfections. And so in optimization, on real quantum annealers, you don't always get the ground state. And for optimization, that's a problem, getting this distribution of states. But then in machine learning, you're often interested in sampling. And so having a distribution of states is actually a good thing. So we were asking the question, can we take advantage of this distribution? Is it Boltzmann-like enough to calculate some of the quantities we need to compute this gradient? And Guillaume already mentioned that the way you train this, you compute the gradient, the log likelihood. This is a classical Boltzmann machine, but the math is very similar. So you end up with this intractable term. And so the idea is to use the quantum annealer as a sampler to estimate this intractable term. So, here's my, all right. Okay, so here's the formula for the log likelihood, and the second term is basically the derivative of the partition function. So it's classically intractable. So the idea is this hybrid algorithm where the overall iteration is running classically, but then on each update cycle, we use the D-Wave machine as a sampler to estimate this term, and we iterate, and we improve our weights. And so we tried this on a fairly small example. It's this MNIST data set, which has already been mentioned. So the real training images are handwritten digits, and they're 28 by 28 pixels. But then to fit them on the 500 qubit D-Wave machine we had at the time, we coarse-grained these images down to 32 superpixels, which was just the right size to fit using this embedding. And so the other attractive thing about these bipartite graphs in restricted Boltzmann machines is that they do embed relatively efficiently on the chimera lattice of the D-Wave. And so, so it is a bit expensive. We had to chain qubits together to achieve this bipartite connectivity. But on this chip, you could do an RBM with 32 visible and 32 hidden nodes, so a 64 variable problem. So compared to other sizes of problems I was trying to embed on the D-Wave, that was actually, relatively speaking, a very efficient use of the chip. So it was also attractive from that point of view. And finally, this whole process is very forgiving of errors. And in fact, in some deep learning training methodologies, you actually introduce noise because that prevents overfitting. And so noise can be a good thing. So for all these reasons, this was an interesting test bed to try quantum computing and machine learning. And we got surprisingly good results. So what we found is that using this hybrid method, you could actually train to the same accuracy with much fewer iterations. So, not real speed up in terms of wall clock time, but definitely, in terms of cutting down the number of overall operations, like I was saying, there does seem to be something there. And this was strictly empirical, and so we didn't know if this was really a quantum effect, if it was due to tunneling or extended states or just some artifact. But folks at D-Wave, for example, and Mohammed and the group there have really improved our understanding of what's happening here. And also, I should mention that from the gate-based standpoint, Nathan Qubit devised a similar algorithm where you can prepare a quantum Gibbs state, similar to what was mentioned earlier. And he showed that you could do a similar training with rejection sampling. In that case, he was actually able to prove that the algorithm is faster. So there seems to be something there in terms of this using quantum computers to train these Boltzmann machines. So, but these are very small examples. And so if you compare to these huge networks that people are already doing classically, so like it's not unusual to have a network with like 1 million nodes and 1 billion parameters. So it's hard to imagine scaling up in the foreseeable future an all quantum analog to that. But we really want to look at possibilities of hybrid architectures where we could maybe use a quantum computer to make things more efficient. And so on the QEO program, well, one of the ways we're looking at that is to maybe relax the requirement on that full bipartite connectivity. And so it seems plausible that in the near term, we will have annealers that have, say, a degree per qubit of somewhere between 10 to 15 in the graph. We think we can do that in QEO. D-Wave has plans for a new architecture, as we heard, which will have higher connectivity, and I think the Google quantum annealer will also have similar type of connectivity. So if we could effectively train neural networks with sparser representations of the Boltzmann machine, then that would certainly help. And so I have an experiment running right now on this middle network. And so this is a range of connectivity here. So the full connectivity, full bipartite graph, that's the paper I already talked about. And then the other extreme is the current D-Wave chimera, which is very sparse. And actually, there were studies by some famous machine learning people's groups, Bengio's group and De Vries' group, a number of years ago, where they did simulations of the D-Wave, and they found that these really sparse networks are not very smart. But, and then we were able to get good results with this full bipartite graph. So the question is there some intermediate level of sparsity where you can also get good results, but with less overhead? And so I have an experiment running right now, and I may have some preliminary results. I'll give more details about this, and maybe the preliminary results in the QEO review tomorrow morning. So those of you on QEO, stay tuned for that. And then the other way we could maybe scale this, and Walter's going to talk about this later today, is this idea of hybrid quantum classical, not just in the algorithm, but in the actual representation of the neural network model. So there's this idea of the variational autoencoder, which Walter will talk about, or also the quantum-assisted Helmholtz machine, which Alejandro and the NASA team worked on. And so both of them have this general architecture where you have a classical deep neural network, similar to what I already described, but then you have this small dimensional latent space, which is where the quantum computer comes into play. And then, thank you. And then you fan back out classically as well. So the left-hand side you can think of as an autoencoder or as sparse coding or compressive sensing. And then on the right-hand side you have your decoder, your reconstruction. And so there's some really interesting work looking at these hybrid models like this, which you'll hear more about today. And we're very interested in looking at this type of architecture as well. So my intern, Jarrett, who's in the room, yeah, he's working on some approaches like this for us as well. Oh, and then one just real quick sidebar. The other thing I've been working on a lot lately is this notion of bias measurement and correction. So you heard already in this conference about noise, and usually we think of noise as being, Gaussian mean zero, but then there are also, on real annealers, small systematic biases, and that can affect your statistics. And so D-Wave does a great job of calibrating the chip initially, and then they have this hourly computation process to correct for flux drift. But what I found is that it does make some difference in the statistics. So again, the NASA team has published this bias measurement and correction approach, and so D-Wave's been very helpful in coming up with a feature where I can actually turn off this hourly compensation and use this NASA method instead. I had a poster last year at the D-Wave Qubits conference about that, and so this is something that from a technical implementation standpoint, it's very helpful when you're doing these long-running machine learning experiments where you want consistent statistics from hour to hour. So just to summarize, is quantum annealing useful for machine learning? Still an open question, I think. But this area of neural networks, for the reasons I mentioned, it is an attractive potential application. And so, it maps relatively well to the architecture. It's error tolerant. And, the current classical methods are very compute intensive. So there's an opportunity to improve on the classical. And then as the qubit connectivity improves, the overhead for doing these mappings will decrease. We're looking at sparser models. And then, I think the big promising area is these hybrid quantum classical architectures. So. Okay, that's it. Any questions?
All right, thank you very much. I think we already have our first question. Oh yeah, let's start in front.
Hi, so it's not immediately obvious to me why we should expect quantum circuits to be good for mimicking the action of neural networks. If neural networks are, many to few kind of mappings and they're irreversible, they're compressive, whereas quantum circuits are, reversible, unitary. And so it seems to me like you have to superimpose the compression aspect, by some loss function, or it's not obvious to me why you should expect, one to map well into the other, as you said at the end there.
Yeah, no, that's a fair question, and I guess it's maybe not the right way to look at this overall network as being some kind of circuit or unitary transformation. And so like we say, really it's especially in this hybrid architecture, it's the quantum computer is essentially representing this latent space, and you're really using it for sampling. And so the question is, if you want to do this kind of sampling or estimation, how would you do that classically? And probably you do have rugged energy landscapes, involved in that Hamiltonian. And so, as we've heard, there are, in some cases, advantages in exploring those landscapes quantumly due to tunneling or extended states and things like that. So, so I think like that's the way that I look at that, if that helps.
All right, I think we have time for one more quick question from the gentleman in the blue shirt.
Thanks. Hi, Steve. Yeah, I liked your talk a lot. So I think these explorations of at what degree of sparsity is still useful, but do you have a sense of two things? The scale at which it would start approaching commercial utility, and the errors of the distributions you're getting relative to, say, the ground truth that would be useful? Because we're looking at things like L1 errors in our distributions now and trying to get an idea of how good that has to be useful, and the scale at which you'd ultimately have to get.
Yeah, I think it's still too early to say quantitatively either question, like what connectivity you need, or how well you can scale these. And so, so definitely you would need a lot of compression to do, say, the approach Walter's going to talk about, and compress all the way down from, say, gigapixel images down to some latent space you can represent on a quantum computer. Right? So, so I don't think we're there yet, but I think we're close. And one of the things that's encouraging is that it's really not the overall size of these networks; it's more like the size of the layers that is the key size when it comes to these neural networks. So,
all right.